Materials for use in vacuum are materials showing very low rate of outgassing in vacuum, and, where applicable, tolerant to the bake-out temperatures. The requirements grow increasingly stringent with the desired degree of vacuum achievable in the vacuum chamber. The materials can produce gas by several mechanisms. Molecules of gases and water can be adsorbed on the material surface. Materials may sublimate in vacuum. Or the gases can be released from porous materials or from cracks and crevices. Traces of lubricants, residues from machining, can be present on the surfaces. A specific risk is outgassing of solvents absorbed in plastics after cleaning. The gases liberated from the materials not only lower the vacuum quality, but also can be reabsorbed on other surfaces, creating deposits and contaminating the chamber. Yet another problem is diffusion of gases through the materials themselves. Atmospheric helium can diffuse even through Pyrex glass, even if slowly. This, however, is usually not an issue. Some materials might also expand or increase in size, causing problems in delicate equipment. In addition to the gas-related issues, the materials have to maintain adequate strength through the entire required temperature range, maintain their properties, be possible to machine, and if possible not being overly expensive. Yet another concern is the thermal expansion coefficient match of adjacent parts. Materials to avoid: materials outgas by two mechanisms, release of absorbed and adsorbed gases, and evaporation of the material itself. The former can be reduced by a bakeout, the latter is an intrinsic property of the material. Some outgassed materials can deposit on other surfaces, contaminate the vacuum system and be difficult to get rid of. The most common sources of trouble in vacuum systems are cadmium, often present in the form of cadmium plating, or in some soldering and brazing alloys; zinc, problematic for high vacuum and higher temperatures, present in some construction alloys, for example brass and some brazing alloys. Tends to poison hot cathodes and form conductive deposits on surfaces. Magnesium, PVC, usually in the form of wire insulation, paints, lead and antimony used in some soft solders and outgassing at higher temperatures. Many plastics, namely many plastic tapes. Fiberglass composites, for example micarta and G30, should be avoided. Even Kapton and Teflon are sometimes advised against. Various residues, for example flux from soldering and brazing, and lubricants from machining. Thorough cleaning of the parts is important. Getting the outgassable residues from tight crevices can be challenging. A good mechanical design that avoids such features can simplify one's life. Materials for vacuum use. Metals. Austenitic stainless steels are the most common choice for high vacuum and ultra-high vacuum systems. Not all alloys are suitable. For example, the free machining 303 steel contains sulfur, which tends to outgas. Alloys with good weldability under arc welding are usually chosen. 304 stainless steel is a common choice of a stainless steel. 304L stainless steel, a low-carbon variant of 304 steel, is used for ultra-high vacuum systems. 347 stainless steel does not accept high polish. 321 stainless steel is chosen when low magnetic permeability is needed. Mild steel can be used for moderate vacuums above 10A6 torr. Outgassing can be lowered with suitable plating. It has high permeability to hydrogen and tendency to rust. For use it should be thoroughly outgassed in vacuum. Aluminium and aluminium alloys are another class of frequently used materials. They are well machinable and have low outgassing, unless the alloys contain higher proportion of zinc. The parts must not be anodized, as the oxide layer traps water vapor. Aluminium and its alloys have low strength at high temperatures, distort when being welded, and the copper-containing ones are poorly weldable. Aluminium wirings can be used as cheap gaskets in demountable seals. Aluminium has high thermal conductivity, good corrosion resistance, and low solubility of hydrogen. Loss of strength at high temperatures limits its use in bakeable applications, but aluminium is advantageous for large-size systems due to its lower weight and lower cost than stainless steel. Use of aluminium is limited by difficulties in its welding and brazing. It can be used for X-ray windows. Aluminium bronze is a material looking and machining similar to brass. It is not susceptible to galling, which makes it suitable for sliding fits against stainless steel. Nickel is widely used in vacuum technology, for example as mechanical parts in vacuum tubes. It is relatively low cost, can be spot welded, can be easily machined, has high melting point and is resistant to many corrosive fluids and atmospheres. Its potential drawback is its ferromagnetism, which restricts applications that would be influenced by magnetic fields. Nickel alloys, for example cupronickel, beryllium is used primarily for X-ray windows. Oxygen-free copper is widely used. It is easily machined and has good corrosion resistance. It is unsuitable for bakeable vacuum envelopes due to its tendency to oxidize and create scales. Copper rings are used in demountable seals. Normal copper is unsuitable for high vacuum as it is difficult to outgas completely. Copper is insensitive to hydrogen and impermeable to hydrogen and helium, has low sensitivity to water vapor, but is attacked by mercury. Its strength falls sharply above 200 degrees Celsius. Its vapor pressure becomes significant at above 500 degrees Celsius. Brass is suitable for some applications. It has good corrosion resistance. Its zinc content may cause problems. Zinc outgassing can be reduced by nickel plating. Indium wire is used as a gasket in demountable seals. Gold wire is used as a gasket in demountable seals for ultra-high vacuum. Platinum is a highly chemically inert material with high cost and low outgassing. Zirconium is corrosion resistant. It has low production of secondary electrons, so it is used as a coating of areas where reducing their production is important. It is used for neutron windows. It is costly and scarce, its uses are therefore limited. Zirconium and zirconium hydride are used for gettering. Tungsten is often used in high-temperature applications as well as for filaments in electron-ion optics. It becomes brittle from work hardening when mechanically deformed, or subjected to very high temperatures. Molybdenum and tantalum are useful for high-temperature applications. Titanium and niobium are good materials. Solders are sometimes unavoidable for soft soldered joints. Tin lead solders can be conditionally used when the apparatus is not to be baked and operating temperatures aren't elevated. A better choice for vacuum systems is the tin-silver eutectic, SN95 Ag5. Its melting point of 230 degrees Celsius allows bakeout up to 200 degrees Celsius. A similar 95-5 alloy, SN95SB5, is unsuitable as antimony has similar vapor pressure as lead. Take care to remove flux residues. Brazing alloys are used for joining materials by brazing. Care has to be taken while choosing the alloys, as some elements tend to outgas. Cadmium and zinc are the worst common offenders. Silver, a common component of brazing alloys, can be problematic at higher temperatures and lower pressures. A silver-copper eutectic, named for example Kusyl, is recommended. A superior alternative is a copper-silver tin alloy called Kusyl tin. Copper-silver phosphorus alloys, for example Silphos, are also suitable. Plastics Some fluoropolymers, for example polyvinylide and fluoride, are suitable for use in vacuum. They have low outgassing and are tolerant to higher temperatures. Polytetrafluoroethylene is commonly used inside of vacuum systems. It is self-lubricating, a good electrical insulator, tolerant to fairly high temperatures, and has low outgassing. It is not suitable for barrier between vacuum and atmosphere, as it is somewhat permeable for gases. Ceramics is a superior choice, however. Polyethylene is usable but requires thorough outgassing. Nalgene can be used as a cheaper alternative for bell jars. Vespol polyamide is very expensive, but machines well, has good electrical insulator properties and is compatible with ultra-high vacuum. PVC, despite its high outgassing rate, can be used in limited applications for rough vacuum lines. Nylon is self-lubricating but has high outgassing rate and high affinity to water. Acrylics have high outgassing rate and high affinity to water. Polycarbonates and polystyrene are good electrical insulators with moderate outgassing. PEEK has relatively low outgassing values. Kapton is a type of polyamide film, has very low outgassing. Kapton is discouraged if a ceramic alternative can be used. Some elastomers have sufficient vacuum properties employed for vacuum O-rings, NBRs commonly used for demountable vacuum seals. FKMs, is used for demountable vacuum seals. It is better for lower pressures than nitrile rubber and chemically much more inert. It is bakeable to 200 degrees Celsius. FFKM's very low outgassing similar to Teflon and withstands baking temperatures up to 300 degrees Celsius, while chemically one of the most inert sealing elastomers. Glasses and ceramics borosilicate glass is often used for smaller assemblies and for viewports. It can be machined and joined well. Glasses can be joined with metals. Porcelain and alumina-ceramics, when fully vitrified and therefore non-porous, are excellent insulators usable up to 1500 degrees Celsius. Some ceramics can be machined. Ceramics can be joined with metals. Maca is a machinable ceramic that is an excellent alternative to alumina, as the firing process of alumina can change the dimensions and tolerances. Lubricants lubrication of moving parts is a problem for vacuum. Many lubricants have unacceptable outgassing rates, others lose lubricating properties. Vacuum greases are greases with low outgassing. Critox is a flue leather-based vacuum grease, useful from -75 to over 350 degrees Celsius, not flammable even in liquid oxygen, and highly resistant to ionizing radiation. Polyphenol ether greases, Turlube, a brand encompassing a range of lubricating oils based on perfluoropolyethers. Dry lubricants, can be incorporated in plastics as fillers, as a component of sintered metals, or deposited on metal, ceramic and plastic surfaces. Molybdenum disulfide is a dry lubricant usable in vacuum. Tungsten disulfide is another dry lubricant usable in vacuum. It can be used at higher temperatures than MoS2. Tungsten disulfide used to be significantly more expensive, but rise of prices of molybdenum disulfide brought them to a comparable range. Usable from -188 to +1316 degrees Celsius in vacuum, from -273 to +650 degrees Celsius in normal atmosphere. Hexagonal boron nitride is a graphite-like dry lubricant used in space vehicles. Adhesives Torseal, or its generic equivalent ALll 1C, is an epoxy with resin and hardener for use in vacuum environments. It will begin to degrade at high temperatures but otherwise is very stable with very little outgassing. Other vacuum-rated epoxies are also available. Materials for use in space. In addition to the concerns above, materials for use in spacecraft applications have to cope with radiation damage and high-intensity ultraviolet radiation, thermal loads from solar radiation, radiation cooling of the vehicle in other directions, and heat produced within the spacecraft systems. Another concern, for orbits closer to Earth, is the presence of atomic oxygen, leading to corrosion of exposed surfaces. Aluminium is an especially sensitive material. Silver, often used for surface-deposited interconnects, forms layer of silver oxide that flakes off and may erode up to a total failure. Corrosion-sensitive surfaces can be protected by a suitable plating, most often with gold. A silica layer is also possible. However, the coating layer is subject to erosion by micrometeoroids. References: Choosing the right vacuum materials.